Welcome to the Deep Dive. Today we're kicking off something a bit special. This is the start of our CSWIP 3.1 exam prep series.
That's right. CSWIP 3.1, the Welding Inspector Certification,
Yeah.
level 3.1. Really crucial for anyone serious about inspection.
Absolutely. And our mission here is, well, pretty straightforward. We want to help you get ready for that exam. We'll be taking multiple choice questions, pulling them apart, really, not just looking for the right answer, but digging into the why, understanding the actual knowledge behind it.
Yeah, it's about getting that core understanding, turning tricky subjects into something, clear and usable, not just memorizing.
Exactly. So let's get started on this deep dive together.
Sounds good. This isn't just about passing an exam, though that's important. It's about building a solid foundation for your whole career. Safety, quality, it all ties in.
Well said. Okay, first question, we're jumping right in, and this one focuses on a specific technique in TIG welding.
TIG, tungsten inert gas, known for those really precise, clean welds.
Right. So question one is, a fusible insert for TIG welding helps. Okay, reduce porosity. B, give controlled root penetration. C, avoid the need for a back purge. D, by acting as a backing for the root run.
Okay. This is interesting because it hones in on, achieving that perfect root pass in TIG and getting the root right. Well, that's fundamental for the weld's strength, isn't it?
It really is. Now, I think some people might just think, oh, an insert, that's just like extra metal. How does it do more than just add material? Why is controlled root penetration the key benefit here, maybe over something like reducing porosity?
Good question. The correct answer is B. Give controlled root penetration. See, a fusible insert isn't just random filler. It's engineered, often pre-shaped, designed to melt very predictably into the weld pool right at the root.
Ah, okay, predictably.
Exactly. That consistent melting gives you a uniform amount of material right where you need it, helps keep the molten pool stable, and the result is this really smooth, uniform root bead, and crucially, consistent penetration.
Right.
That control is just vital for structural integrity, obviously, but also for passing inspections. Think about aerospace, nuclear.
Yeah.
You can't have tiny inconsistencies there.
So that consistency is the real game changer. It's not just about having more metal, it's about how it goes in. Does that mean less rework, maybe? More predictable results on big jobs?
Oh, definitely. The impact is huge. That level of precision, it allows for the kind of reliability you need in those critical sectors we mentioned. It sort of takes some of the guesswork out for the welder on that critical root pass, reduces the chance of defects like suckback or, too much penetration. So yes, fewer repairs, fewer rejections, a better outcome from the start. And just quickly on the other options, a good root helps avoid porosity, sure, but that's not the insert's main job.
Indirect benefit.
Exactly. And it definitely doesn't replace a back purge. You still absolutely need that purge gas to protect the root from the air, especially with reactive metals. And option D, acting as a backing.
Well, it adds material, yeah, but the control it offers is the key thing. That's different from just, say, a copper backing bar.
That distinction is fascinating. Adding material versus actively controlling how it goes in, that's a critical point for TIG, isn't it? Really science meeting skill.
Precisely.
Okay, so from the tools that help precision, let's shift focus a bit. Let's talk about the weld metal itself, its chemistry. Our next question gets into the material science behind the weld properties.
Ah, yes, the electrode.
Question 2. The chemical composition of the weld metal deposited by a CMN steel MMA electrode is usually controlled by a core wire composition, B, additions in the flux coating, C, iron powder in the flux coating, D, dilution from the base material.
Right, so CMN steel, carbon manganese steel, super common, and MMA manual metal arc or stick welding. Very versatile process. Understanding how that electrode actually delivers the final weld properties, that's fundamental stuff. It's a mix of things, but one part plays a lead role. Okay, so my first thought might be, well, the core wire is the metal, right? Surely that dictates the chemistry. Can you explain why the flux coating, the stuff that burns off, actually has more control? That seems a bit counterintuitive.
It does seem that way at first glance, but the answer is definitely B, additions in the flux coating. Here's the thing. While the core wire provides the, let's say, base iron and some carbon manganese, it's that flux coating that's packed with all sorts of clever stuff. Alloying elements, maybe extra manganese, silicon, perhaps even nickel or chromium, depending on the electrode type, plus deoxidizers to clean the weld pool, slag formers to protect it, sometimes even materials that generate shielding gas.
Wow, okay.
And these additions are specifically designed to transfer across the arc into the molten weld pool as the flux consumes itself. So they massively influence the final chemistry. That's how manufacturers create electrodes for specific strengths, toughness, corrosion resistance, far beyond what the simple core wire could do alone.
That's actually incredible engineering packed into that coating. It means you can essentially create high-performance alloys right there at the weld joint, even out in the field with MMA.
Exactly. It bridges that gap between lab-controlled metallurgy and practical on-site welding.
So what about the other options then? The core wire must still matter.
Oh, it contributes, absolutely. It's the base. But the flux coating has the dominant controlling influence on the final specific chemistry. That's the key word, controlled. Iron powder, option C. That's mainly about deposition rate. More powder usually means you put down weld metal faster, it affects efficiency, but not the primary chemical control.
Right, fills the joint quicker.
Yeah. And option D, dilution from the base material. That's definitely a factor in the final weld metal composition because the base metal melts and mixes in.
Okay.
But the question asks, what controls the composition from the electrode itself, how the electrode is designed to deliver a specific chemistry, and that's the flux.
I got it. So the flux coating is like the recipe card for the final weld metal.
Yeah.
A crucial concept for inspectors.
Absolutely fundamental.
All right, let's change gears again. We've talked processes and materials. Now let's talk about the inspector's role, what you actually do. Question 3. A duty not normally undertaken by a welding inspector is to A. Check the condition of the parent material. B. Check the condition of the consumables. C. Measure residual stress. D. Check calibration certificates.
This is important. Understanding the scope of the job, where your responsibilities start, and crucially, where they stop, where other specialists might need to step in.
Yeah, the inspector does a lot, but they don't do everything. Looking at these options, which one typically falls outside the standard CSWIP 3.1 welding inspector's day-to-day tasks, and why?
The answer here is C, measure residual stress. Measuring residual stress, that's a whole different ballgame. It's highly specialized.
How so?
Well, that usually requires specific, often quite complex equipment. Things like X-ray diffraction, maybe neutron diffraction, specialized strain gauging techniques, and it needs expertise you typically find with metallurgists, material scientists, or maybe very advanced NDT specialists.
NDT being non-destructive testing.
Right. It's more like forensic analysis, trying to understand the locked-in stresses within the material. It's not part of the routine visual checks, process monitoring, and basic quality control that a CSWIP 3.1 inspector focuses on.
So definitely not something you just whip out a standard gauge for.
Absolutely not. Trying to do it without the right gear and know-how, you'd likely get meaningless results. Or worse, miss a critical issue. It's about knowing your lane, really.
Knowing your lane, I like that. So the other options, checking parent material, consumables, calibration certs, those are firmly in the inspector's court.
Oh, completely. Let's run through them. Checking the parent material. Essential. Before any welding starts, you need to check the material is correct, undamaged, dimensions are right.
Makes sense.
Bolus, checking consumables. Absolutely critical. Are they the right type? Stored correctly, think keeping MMA electrodes dry in an oven. Are they undamaged? Huge impact on quality. And A, checking calibration certificates. Foundational for quality assurance. Any measuring tools the inspector uses, or that the welders use gauges, temperature sticks, calipers, whatever, you have to know they're accurate. Checking those calibration certs confirms they've been tested and are reliable within their due date. No good inspecting if your ruler is wrong, right?
Your measurements have to mean something. So understanding those boundaries is key for doing the job effectively and safely. Ensures the right expert is on the right task.
Precisely.
Okay, moving on. Let's tackle a classic welding defect. One that every inspector needs to be able to spot. Lack of sidewall fusion.
Yes. A common but critical one.
Question 4. Lack of sidewall fusion. A. Is the most susceptible in W butt welds. B. Is never found in single V butt welds. C. Is the most susceptible in double V butt welds. D. It is not normally a defect associated with the MMA welding process.
This is interesting because it highlights how the actual shape of the joint, the geometry, can make certain defects more likely. Understanding this helps you know where to look extra carefully, like predicting weak spots.
Yeah, lack of sidewall fusion. It's basically where the weld metal doesn't properly fuse to the side of the joint, right?
Yeah.
So thinking about joint shapes, which of these weld preps makes it easiest for that defect to rear its ugly head?
The correct answer is A, is the most susceptible in W butt welds. And the reason is that U-groove shape. Especially a W. You often have quite narrow roots and really steep sidewalls.
Right, almost vertical sides sometimes.
Exactly. And getting the molten weld metal to flow nicely, wet out, and fuse completely onto those steep faces can be really tricky. Imagine pouring honey into a deep, narrow crack. It might not reach everywhere easily. It takes very precise control of the arc, the travel speed, the heat.
I see.
If the welder doesn't direct the heat properly onto those sidewalls, or if the pool isn't quite fluid enough, it's easy to leave little areas unfused along the groove face, hidden sometimes. I remember inspecting a pressure vessel with W joints once. Finding the subtle lack of sidewall fusion required some careful visual work and confirmation with NDT. It wasn't obvious just looking at the surface cap.
It sounds like detective work. And if you miss it, what happens down the line if lack of sidewall fusion isn't caught?
Well, it's a major problem. It's a significant discontinuity. Essentially, the weld isn't fully joined to the parent metal along that face. That dramatically reduces the strength of the joint, especially its ability to handle fatigue or repeated stress. It acts like a built-in crack starter. It can definitely lead to failure under load.
Critical stuff. Okay, let's quickly look at the other options then. Why are they wrong?
Right. Option B, never found in single V butt welds. Absolutely wrong. You can definitely get lack of sidewall fusion in a V groove if your technique or parameters are off. Bad angle, too cold, too fast. Option C, most susceptible in double V butt welds. Generally not considered most susceptible compared to the U groove. While it can happen in a double V, that steeper, tighter U profile often presents the bigger challenge for fusion. And D, not normally associated with MMA. Completely false. Lack of sidewall fusion is a common potential defect in many processes, including MMA. If the welder doesn't maintain the right arc length, travel speed, or current, it can happen easily.
So understanding how joint design interacts with potential defects is vital. Tells the inspector where the higher risks might be, knowing where to look.
Exactly. It guides your inspection strategy.
All right, last question for this session. This one is about terminology, getting the language right.
Always important in this field. Precision in language matters.
Question 5, compound welds. A, always contain full penetration butt welds. B, joints which have combinations of welds made by different welding processes. C, combinations between two different weld types. D, all of the above.
Yeah, terminology. Being precise helps everyone communicate clearly. Avoids misunderstandings, which, as we know, can be costly or dangerous in welding.
So the term compound weld, what exactly does that describe? What's the key feature, and maybe where does confusion sometimes creep in with similar terms?
The correct definition here is C, combinations between two different weld types. A compound weld usually means you have more than one distinct type of weld within the same joint preparation. The classic example is combining a butt weld with a string weld.
Okay, like in the same groove.
Yeah, for instance, you might have a partial penetration butt weld deep in the joint and then a fillet weld layered over it, maybe on the inside or outside corner. The purpose could be to add strength, ensure it's sealed properly, or maybe accommodate a specific joint geometry. But the key identifier is that mixed combination of different weld types. Butt and fillet is common.
It really underscores how important using the right terms is, doesn't it? Like, everyone needs to be on the same page. Getting this wrong could lead to someone misunderstanding the joint design or the inspection requirements.
Absolutely. If the drawing calls for a compound weld and you're only looking for a butt weld, you've missed half the picture. Let's quickly rule out the others. AWO. Always contain full penetration butt welds. Nope.
Yeah.
Can definitely involve partial penetration butts, and it's the combination that matters, not just the butt weld itself.
Right.
Combinations of welds made by different welding processes, that describes something different. We usually call that a hybrid weld or maybe multi-process weld. Think like laser welding, followed by TIG in the same joint. Different processes, not necessarily different weld types in the sense of butt versus fillet. It's a subtle but important distinction.
I see. Process versus type.
Exactly. And since A and B are wrong, D, all of the above, is obviously out too.
Okay, that clears that up nicely. Precision in language is paramount. Well, what a session. We've covered quite a bit of ground there. From fusible inserts in TIG, the chemistry magic in M&A flux, what an inspector does and doesn't do, lack of sidewall fusion, and finally, getting our terms right with compound welds. All really vital stuff for anyone prepping for that CSWIP 3.1 exam. But more than that, just crucial knowledge for being a competent inspector out in the real world.
That's right. And remember, like we said at the start, truly understanding the why behind the answers. That's what really makes the knowledge stick and become useful.
Absolutely. Makes all the difference.
And maybe a final thought for you, the listener. As you master these details, think about the bigger picture. How does getting this right contribute? It's not just about passing a test. It's about ensuring the safety and reliability of bridges, pipelines, power plants, structures people depend on every day. Every detail you understand, every check you perform correctly adds to that overall safety net. It's a significant responsibility.
That's a great point to end on, a really important perspective. Well, thank you so much for joining us for this first deep dive in our CSWIP 3.1 exam prep series. We hope you found it valuable. We'll be back soon with more questions to dissect. Until then, keep studying, keep asking questions, and stay sharp.